So my name's Mike Milner. I've been really interested in everything going on in space for my whole life, but I've kind of become particularly interested as we've started doing more and more commercial activity in space. And largely that's been kind of my interest in SpaceX because they're doing so many cool things in space. And I really got interested in this when they were working on the Starlink project. And I like talking about space. I like working on space. So I decided I was going to try to launch my own satellite into space. Okay. This is the most often or common response I get when I tell anyone that I'm doing this. So I figured this presentation can kind of walk through the story of how I've reached this point and how far I've gotten, let's say. So since the start of the pandemic, that's when I kind of got into this. I decided since we're all stuck at home anyway, I was going to start doing some YouTube videos about space. So I've, 55 videos so far. So I'm not a regular video maker. I think even these ones are a couple months old now. But whenever I've got something I like to share, I like to put up a video. And I've been doing this a long time, primarily talking about things to do with Starlink. But then Starlink actually launched and people started getting it, and it's all over the place. Anywhere in the world you want high-speed internet, you can get Starlink and it's there. So there's less exciting stuff for me to talk about. So I was kind of thinking, what can I do next on the channel that's going to be interesting for people? It was actually Steve over there who thought of the idea. One of my videos very early on, I was talking about how you communicate with satellites in space. I've got a big antenna that'd be like holding your hand and wave around, and you can get amateur radio satellites. It seems like I really like that one. Maybe you should build your own satellite. So after some careful thinking, I decided, what the hell, how hard could it be? So is it even possible? And Sandy touched on this a little bit, but I think the biggest trend that we're seeing right now, the biggest limiting factor to getting things into space has always been the cost of launching them into space. If a rocket launch costs hundreds of millions of dollars, then the cost and effort into building the satellite almost becomes a small matter, right? Who cares if the satellite costs 10 million if it's going to cost you 100 million to get it up there? But over the past few years, you can see for basically all of history of space, the cost of getting mass into orbit has kind of stayed around this middle zone. Right up until Falcon 9, Falcon Heavy, and if Elon Musk follows through and gets what he's planning for, a Starship and Super Heavy is going to dramatically reduce this cost of getting mass into orbit. And this is a logarithmic scale as well. So these things down here are a lot cheaper than the things up there. So we kind of saw this similar trend with the internet, right? Way back in the early days of the internet, it was, well, what's the internet for? No one, it's too hard, too complex, too slow. But it got better. And as the internet got better, people started doing more and more things on it. So I figured space is probably going to end up going the same way. As it gets cheaper to get things into orbit, there's going to be more and more people doing it and finding new ways to make value. So I figured I want to get in on this action. So what is orbit? So Sandy touched on a bit of this. Low Earth orbit, kind of from there to there. This is around maybe 500 to 1,500 kilometers straight up. Like all the doves that Sandy mentioned, these are in low Earth orbit. A lot of Earth imagery is in low Earth orbit because you want to get close to the thing you're taking a picture of. Next up, you've got medium Earth orbit. And to be honest, there's not a ton that's happening there on the commercial front. The biggest thing using medium Earth orbit that most people know about is GPS. the Global Positioning System satellites are in medium Earth orbit. And you'll see these are all kind of fuzzy bands because these aren't like a single fixed altitude. They're kind of a range, right? Like all of this is low Earth orbit, all of this is medium Earth orbit. The one that is fixed is geostationary or geosynchronous orbit. And the reason it's fixed is because it's an exact distance from the surface of the Earth where the rotational speed of the satellite exactly matches the rotational speed of the Earth. So you're probably familiar with satellite television, although maybe less familiar if you're younger. But when I was young, satellite TV was these great big giant satellites people had in your backyard, and you'd aim it, point it up into space, and then that was it. It never moved again. That was pointing at a particular what's that, longitude in orbit for the geostationary satellite of your satellite TV provider. The nice thing is then you didn't have to move that. Low Earth orbit, then you have the issue like Sandy was talking about, where these satellites are always going around the Earth and you don't need one ground station, you need like hundreds all over the place. So this geo orbit is super important, super critical, but kind of becoming less so now that we're getting better at making use of low Earth orbit. Like the Starlink satellite constellation, high-speed internet, it's using low Earth orbit. For my project, low Earth orbit, there's a few benefits there. One, it's cheaper to get there. Two, it's easier to burn up in the atmosphere, which maybe sounds like a bad thing, but if you're launching a satellite and it breaks up there, you don't want to be responsible for space junk that's going to sit there for decades or centuries. So low Earth orbit, these things just naturally will fall out of orbit in like 5 years or something like that. So it's kind of safer from that perspective. Just as a side note, there's also some other cool orbits around the sun. So everything that I talked about, even that geostationary orbit, would be in this tiny little sliver around the blue ball of Earth. And this is not to scale, of course, but everything that we do is way inside the orbit of the moon. I mean, science missions generally go further, but the orbits that I talked about previously. But you can also orbit around the sun. And the notable positions are these L points, Lagrange points. And if anyone's watching sci-fi TV, you might have heard of the three-body problem. These Lagrange points are actually special cases of the three-body problem. So you've got sun, Earth, and satellite, three bodies. And at these particular points, the three-body problem that they make such a big deal about in the movie is actually a quite simple solution. These points, if you are in one of these points, you're in a stable orbit. So you don't have to use much thruster power to stay where you are. A notable one these days, way out here in L2, is the James Webb Space Telescope. So it's orbiting around that L2 Lagrange point. So I'm not trying to get anything into solar orbit, but you know, if the Earth orbit thing works out, that would be a great next step, right? Okay, so I think we know from Sandy's presentations that satellites, in fact, are super complex. Definitely understandable, but there's certainly a lot to something like Sandy described, right? You saw those block diagrams, those charts. There's a lot of effort that goes into making these things resilient and pliable. But I'm not a company, so I don't care about any of that. So what makes a satellite, right? Well, the big satellite out there is the moon. It's just something circling the Earth. So generally, we're saying, okay, that's the moon, but what about artificial satellites? Anybody know what satellite that is? It's an easy question. All right. Technically, I found out it's actually called Sputnik 1. Sputnik just means satellite. So all Russian satellites are Sputnik, apparently. Sputnik 1. And all that it did is go around orbit and send out those beep, 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 right, that you hear in all the videos. Still a satellite. It doesn't have to be complex or doing a lot to be considered a satellite. So I thought, what's my minimum viable satellite? What's the least I could put into orbit that would do something? So I kind of started, well, even something like this. Now, does anyone recognize this from elementary school math class? There's 1,000 little cubes in here. So 10 centimeters by 10 centimeters by 10 centimeters. This is the 1U CubeSat size that Sandy mentioned. Now, technically it's a bit bigger. It has little rails that stick out a little bit, like you see here. But this is the basic idea. Like, this is not huge. But if I could convince someone to put this in their rocket and send it into space, technically I would have launched a satellite into space. But that's not quite enough for what I want to do. So I said, well, what's my minimum? I want to have some kind of a radio on this thing so that it can send a signal back down to Earth just to let me know that it actually made it up there, it's still alive, and it can report some of those status messages that Sandy mentioned. How much battery does it have? Where is it? Just so that I can kind of get that satisfaction that, hey, it's up there, it's doing something. And everything else kind of works back from there. I'd like to have some kind of a command and control so I could actually send it a command to do something. I mean, that's a luxury, I know. But, and then everything else is kind of the bare minimum that you need for that, right? If you're going to have a radio that uses power. When you're in low Earth orbit, for a significant part of the orbit around the Earth, it's going to be in the dark, the shadow of the Earth. So you need some kind of power. Batteries is an easy way to power it when it's on the dark side of the Earth. And if you've got batteries, you want some way to charge them. So you have solar panels to collect the sun's energy, and then charger logic to put that into the battery. So I figured this is the bare minimum that I would need to figure out to get a satellite to do that minimum something in orbit. Now, like I said, this is around that 1U size. Sandy mentioned the 3U size for the Dove satellites. There's also another kind of range of these standard sizes. So this is the 1U, that's the 3U. You can kind of figure out the pattern from there. But they do get quite large. You can imagine 12 of these stacked up. You can put a significant amount of payload in there. And CubeSats are interesting because they are designed to make it easier for people like me, amateurs, to get satellites into space. Because the ultimate control over what gets into space is the launch provider. And usually they are used to launching these big satellites for big companies. So you've got one gigantic satellite, some of these are the size of a school bus, on the top of this rocket in that big fairing portion, and they launch that up. That costs a lot of money, millions of dollars. I don't have millions of dollars. So the idea with the CubeSats, and I think I talk about this a little bit. This is from Cal Poly, and they designed this specification, and you can see it's not that thick. I think it's something like 30 pages. To just standardize the kind of the bare minimum things that you would have to put into your cube to make it safe to ride along with one of those great big giant satellites. So those satellites are huge, but sometimes they have a little bit of extra space, a little bit of extra payload capacity, and they will let you put your CubeSat onto that launch for just a little bit of money, right? We saw the price of orbit go down in that chart there. It's now around $50,000 to put kind of something like this size into space. Ballpark. I mean, I haven't asked official prices yet. So yeah, it's not cheap, and I don't have $50,000 lying around, but it's within the realm of like, hey, a person could do this, or raise money to do this, or I'm hoping maybe get somebody to take pity on me and send it up for free, publicity. I'm a YouTuber, right? We'll see on that. But so the idea is you build your satellite to conform to one of these standard sizes, and then on the rocket they've got these deployers. They call these ones, I think, P-pods. And you can see all it is a box. And inside the box is a pusher plate, that's the technical term, which is just a piece of metal plate on a spring that when the box opens up, the spring just pushes the satellite out. That's as simple as it is. So your satellite just slides into those rails. They stack 3 of them if you're this big. And when it's the launcher is in the right position, it just sends a command to say, open up your door, pops open, your satellites pop into space. And it's kind of as simple as that. I'm going to flick back a couple slides just to show one other little detail. Sandy mentioned this as well, I'm on the rocket, now I'm in space. You can see up on the corners, there's 4 little bunks. Those are little just buttons. So when the satellite is stacked into that P-pod launcher, those buttons are pushed. So the satellite knows that it's in the rocket. Big satellites who are paying full price, they can still have that satellite doing whatever they want while it's sitting in the rocket. Small satellites like this, they want 0 risk to the big satellite. So for small satellites like this, when those buttons are pushed, your satellite has to be completely turned off. No computers running, nothing, it's off. And then when you get launched, those buttons release and you power up. That's to kind of make sure that whatever crazy harebrained satellite I make won't interfere with the main paying customer. So that's the CubeSat size. The next level up, this is SpaceX's ride-share payload user. So SpaceX does not directly offer CubeSat launches. They are just one step above that. They have this sort of a structure. So if you're not paying for the whole rocket, they've got these ride-share missions where they've got this kind of pillar in the middle, and they sell you slots around the outside. So if you want a big one, you can buy one of those big slots up there. I think there actually were some Planet Lab bigger ones on one of the SpaceX transporter missions, if I recall.
PD-1. Yeah.
And then if you want to do a CubeSat, you actually go through a CubeSat launch provider. They buy one of these little chunks, and then you can see kind of there, they've got like 9 of those little launcher things that I mentioned. So 9 launchers, maybe 3 satellites in each. So a whole little collection of CubeSats might be sitting on the bottom there. And you just need to buy one of those squares to get your CubeSat on. This payload user's guide, you can just download it off the internet. It's bigger, it's around 100 pages. But it goes into all the details of what your payload has to do, testing it has to undergo, standards on how to bolt onto these plates, a whole lot of detail on what SpaceX will require you to do to get onto one of their launches. More complex than what I want to do, which is just go into one of those little green launcher boxes. So, differing levels of responsibility. I get this question a lot. Can you just do that? And I'll say I'm early in my investigations. But I always like to go back to the basics. So, what is space law? So first, what is space? Well, there's this magic line, the Kármán line, which is also not strictly defined, but generally accepted to be 100 kilometers up. And the idea is 100 kilometers up is too high for airplanes to fly. And below 100 kilometers is too low for spacecraft. There's too much atmosphere. They just collapse to Earth. So they kind of said, okay, well, this 100-kilometer line, and they call it a line, but really it's kind of a sphere right around the Earth. That 100 kilometers up. Everything above that is outer space. Everything below that is airspace. And everything above it is governed by this Outer Space Treaty, which was, I think, signed into law in 1966, but actually, I think, mainly debated in 1965. And its main concern was around nuclear weapons in space. That's what everyone was really nervous about. So it lays out a few things. No nuclear weapons in space. Any objects in outer space, like the moon, other planets, can't be claimed by any nation. And any other planets can be used for military purposes. It's a few other things as well, but for my purposes, it also lays out that each country is responsible for its own activities in space. And that includes what the country itself is doing, like NASA or the Canadian Space Agency. It includes what any companies located in those countries are doing, and it includes any individuals in those countries. It's where the satellite operator is, not the launch provider. So if I'm in Canada, but I got SpaceX to launch from Florida, I still need to get licenses from Canada, not the United States. There actually is a good story of a company that used an Indian rocket and managed to get their satellites launched into orbit without having any licenses. It caused a bit of a stir. That company, Swarm Technologies, has now been bought by SpaceX. But they had actually sub-CubeSats. They were like 2.5 centimeters high, little pancakes. And it was actually that space tracking agency, I think it's NORAD. Anyway, whatever the space tracking agency was, they said, actually, we're not going to let you launch because we don't know if we can track things that small quickly enough for an operating satellite. But they launched anyway, and it turns out they were able to track it, thankfully, so they know where they all are. And that company went on to launch, I think, the 70 or 80 of those little pancake satellites into orbit. But each country is responsible for its own activities in space. And in Canada, this is governed by ISED, Innovation, Science, and Economic Development Canada. And largely, the main thing people think about when they're talking about satellite authority isn't actually to launch the satellite. It's to get permission to use the frequencies that your satellite will use to communicate with Earth. For me, since I don't have that much money and this is an amateur project, I'll probably end up using amateur radio frequencies, which you can use if your project is entirely non-commercial, which mine definitely is. But I still need to figure out if there's any other licenses I need to launch this or to do this satellite. You've all heard Sandy's presentation. I think this is a huge amount of work, even for my bare minimum satellite. I'm starting from scratch. My goal is to learn about satellites, but not even learn about satellites. I'm an electrical engineer by education. I've done a fair bit of firmware development, embedded systems, but it was years ago, but I really enjoyed it. So I also want to learn, play around with this stuff. So I don't mind if it's a lot of work. I don't mind if this takes me years to do. I'm just going to keep cracking on that. So now I want to share a little bit about my progress so far. What have I done so far? This is, I'm going to get into the props on the table. Okay. Actually, one of Sandy's block diagrams was on the battery management system. So I'm kind of building my satellite from the basics up to higher level. These are 18650 rechargeable lithium-ion batteries. These are the same batteries that were originally used in all the Teslas. I think now they use a bigger cell. But these are considered good by my random Googling on the internet for satellites. And they also have an important characteristic that you can get them UL listed, which is one of the things that is required in that CubeSat specification. So it just means it's certified and hopefully safe to go into orbit. They don't have a problem with operating in vacuum, and they're relatively easy to get, even though for some reason having them shipped in the mail is like a nightmare, apparently. This is just a raw cell, though. So it's not safe to just connect a voltage to this and charge it. You need to actually charge it according to a certain power profile. You need to make sure you don't discharge it too much, you don't overcharge it too much. And that capability, oh, I forgot I got the little holder for it here. So I've got one here, but I'll probably do 4 in the CubeSat, and like Sandy's point there, for redundancy, maybe it'll actually be 2 sets of batteries that are independent. We'll see. And then I'm using, this is an evaluation board. So this is a big board to evaluate a little tiny chip right in the center. And that's just a battery protection circuit. Actually, why don't I pass this around? Everybody take a look. We'll start a series of show and tells. So this is what I'm working on right now, this battery management system. So how do I make sure these batteries can be charged safely, discharged safely? How do I know, how do I estimate like a percentage? Your phone tells you 99%, 60%, but batteries don't have that output. It's just a voltage. You know how much current you put in, how much you take out, so you need to figure that out. That's just the actual battery protection circuit. Then you have the circuit to charge the battery. So that's another chip. And I've got another development board which has the charger IC. Sandy actually mentioned the I2C communication protocol. That's how chips can talk to each other. That chip that's going around can talk I2C to another controller. So I've got the battery protection, I've got the charger, and then I've got this guy here, which is a microcontroller that can talk I2C. So it can talk to multiple other devices. So this is going to be the brain of my battery management system. I think I've got a picture of this. So I think when Sandy asked at the beginning, we didn't have many people who tried embedded development before. So I wanted to talk briefly about that. This little black square in the middle is a microcontroller. It's basically a computer, just a not very powerful one. But compared to computers in years gone by, this is actually super performant. It has a lot of capability built into it. Key for me is those communication protocols. So it has that I2C to talk to those other chips. It actually has a CAN controller to talk to other units in my satellite, eventually when I have other units in the satellite. And because Sandy mentioned that flat sat concept, right? I'm not going to be building this super fast. Most of my time with this satellite is going to be, it's sitting on my desk, not in orbit. So I also wanted it to be super easy to work with, so I decided I would make it USB-C capable. So I could just plug the satellite into my laptop, and it would supply power to charge the batteries and supply communication to program and debug that little chip inside. This little chip, even though it's just so tiny, typically these would be programmed in C, but because I'm on a learning path, I decided I wanted to learn Rust. And Rust is a programming language used in all sorts of places, but one of the things it lets you do is write fairly low-level code. And important to this does not run Linux. It might run one of those real-time OSs that Sandy mentioned, but you need to write in a programming language that doesn't need an operating system. You can kind of do that bare metal. So I had a new microcontroller. This is made by ST Microelectronics. I had a new development tool chain and a new programming language. And if you've ever done firmware development, the first thing you typically do with a new setup is blink a light, right? If you can blink the light, that's like your hello world. And with all these new things, I promptly and for maybe many, many weeks failed to blink that light. So I decided learning all of these new things all at once was maybe a little bit too much. So I scaled back my ambitions. Rust is super complicated to get started with as a beginner. So I said, okay, no more Rust. The rest of the tool chain, though, actually is really good. So this is a little embedded chip. I just plug one USB cable into my computer. And from my computer, using Visual Studio to write my code, I can program the chip. I can do step-by-step debugging of the chip. I can inspect memory in the chip. It's actually really capable. But I remembered we were at one of the side project meetings run through Halihax. And I don't remember if it was you, Sandy, or one of the other guys there, or maybe someone here, but they were talking about Zig, another low-level programming language. So I kind of looked that one up, and it actually said, oh, it's actually a bit easier to get started, not quite as complex as Rust. So I decided to give Zig a try. So now I've got my blinking light working with Zig programming to the ST microelectronics controller here, and it's blinking my light. So then I progress from there. Sandy mentioned as well lots of state machines. My next project was USB-C. So kind of getting a bit lower level. USB-C, one of the big things it can do is called power delivery. It can ask for more power from the supply. So actually here, I'll pass this around too. These aren't giveaways, by the way. They have to come back to me. So when you plug a USB-C cable into your computer or into a power supply, the thing on the other end, there's actually a little protocol that goes back and forth. Hey, here are my capabilities. Oh, I'd like this power. So to make sure my satellite can charge fast, I implemented these protocol specs. So that's all written in Zig. So now when you take, this is a little daughter board that goes on top of the one that's being passed around, and it just has the USB-C port and a little, just some static protection circuitry. But you put this on top of the microcontroller. That microcontroller already has that USB-C protocol for the low-level communication. And now when I plug it into a power supply, it can ask for the full 100 watts that the spec supports. And that can now be used to charge the batteries. So I've got my batteries charging. I've got power coming over USB-C to charge them. That's kind of the foundation of this battery management system. Next, on top of that, you remember the radio communication. So I've also got a little development board, also with one of those ST microelectronic controllers, a different one that has a wireless chipset. This one can actually run on the amateur radio frequencies. I actually, the OpenLST that Planet Labs released, a lot of the parts have been replaced with newer models, newer versions of the chip. And there's still massive supply chain issues. Like they take like 15 months to get delivered. So I figured I'd give this one a try. And what's my last piece? Oh, right, the last little show and tell. Remember I mentioned those buttons? I've actually got some little ones I had ordered here. They're just tiny little satisfying click. But they've got to disconnect the battery, right? It has to be completely turned off. And then I thought, it would be neat if I could show some kind of a status display on the satellite, right? So when it's sitting on my desk, I could see how much battery was in there or something like that. I could see that it was ready for launch. But you can't power a display when the battery's disconnected. So I got one of these little e-ink displays. And the neat thing about them is once you put something on the screen, you don't need to supply power for it to stay there. So I thought, this could be interesting. I could write my status on that little screen, and then you'd load it into the launcher, power off, but I'd still, see a ready to launch mic on space. So that's also going to be connected to that battery management system. All of this is just one of the blocks in Sandy's big diagram of blocks. So I definitely have a lot to do, but the idea is these common elements, so the battery management system, the solar power, the navigation control, all of those are building blocks that will be added in. And those common building blocks, they often call them the satellite bus. So no matter what payload you put into the satellite, that bus is kind of standard. And if your payload needs more power, maybe you'd have more of the battery systems. If it's going to be bigger, you could put more solar panels on it, but the basic building blocks are the same. Which brings me to probably my most asked question, is what will the satellite actually do? So I talked about that bare minimum, right? I want it just to be able to send a signal so that I know it's up there. But in terms of what it will do, I have no idea. Still a work in progress. But I thought it'd be interesting to share a few of the common areas. I think someone asked about space startups, right? There are quite a few space startups coming around. And there's a few classes of things that are kind of popular right now. The first we heard a lot about from Sandy, Earth observation. So this could be optical imagery, hyperspectral imagery, a lot of different frequency bands. Synthetic aperture radar is another big one, like finding things through clouds. Listening to radio signals on plane tracking devices, boat tracking devices. I kind of group those all under Earth observation. There's probably a million more things that people are observing as well. The idea is, up in space, you've got a pretty high level view of the planet, so you can do a lot of different Earth observation things. So that's a possibility. It's notable, though, that to observe the Earth, even if you might accidentally observe the Earth, you need specific additional licensing. So I'm sure Planet, well, obviously they would have to have that license, but anyone who wants to observe the Earth needs to be licensed specifically. So that's in the US and in Canada. Another big element or segment is just communication in general. So this is a very military oriented diagram from the Department of Defense, but just communication in general, right? That company I mentioned, the Swarm Technologies with the little tiny pancake satellites, they're doing communication. For them, it was IoT, things that only needed to send a tiny bit of data once a day or something like that. Could also be companies like Starlink, SpaceX's Starlink, that are giving high-speed internet to people. But the idea is, if you put your antenna really high up, into space, then you can send your signal over a big footprint on Earth. So the highest antenna you can do is, in space. The next area is something called space situational awareness. So we talked about tracking satellites in orbit. So we do that today primarily on the ground with big radar installations, and we just observe things going by and they figure out what those satellites are. But increasingly, we're doing more in space, so there's more interest in keeping track of what's going on in space. So a big interest here is from the US Space Force. They want to know, that Russian satellite released another satellite, what's that satellite doing? Anything that's going on space, the US, anybody would want to kind of keep track of it. This is also extending into other orbits. So what's going on around the moon? How do I know if Russia launches a satellite and it's doing something around the moon? So the US in particular wants to build up this capability of having more types of observation, situational awareness in space. So there's a lot of startups that are in that area. Of course, science, there's always an interest in science. This is the James Webb Space Telescope. A lot of the payloads, particularly on these small CubeSats, are small science payloads. You want to test out a new sensor or a new way of, orienting a satellite. Well, why send up a big one for the test? Send up a little one. Just has to be big enough to hold the sensor and power it, and then you can test it, and when it decays out of orbit, that's fine. So there's a lot of science missions that might use small satellites like this. And then the last one I want to talk about is this kind of space operations. So increasingly, we're launching satellites that are designed to interact with other objects in space. This is a space servicing satellite. So the idea is, particularly those big satellites in geosynchronous orbit, those are really expensive, it costs a lot to get them there, and they need to use fuel to stay in their assigned orbit. So the satellite hardware might still be fine, but it's run out of fuel. Well, what if we could send up a little cheaper satellite that would just fly up, refuel it, and then it would extend the life of that big satellite for another 10 years maybe. Space junk removal is another one. If we've got a rocket fairing that's just circling the Earth and is a danger to other satellites or astronauts or space stations, maybe we can send up a little satellite. It can just kind of grab onto that space junk and just slow it down. There's lots of different ways they might do that, but basically pull it out of orbit so it burns out. Or those big geosynchronous satellites, when they are near end of life, it might push them out past geosynchronous orbit so that they just don't interfere. So there's a lot of things happening with space or satellites rendezvousing with other satellites, including military things, right? What if we wanted to wreck that satellite? That type of thing's happening as well. So that's another big area of interest. But the main thing I really wanted to convey in this presentation is that all of this stuff on the table, there's nothing space particular. Everything I've done so far is basically like a USB power bank, right? Like it's not that complex. There's really nothing happening here that's space specific. It's really accessible if you want to learn more about embedded programming. If you want to learn more about new languages, it's totally something you can do. One of these boards, just with a microcontroller, a development kit, just to try it out, these can be pretty cheap, like 30 bucks. Like the USB cable to plug into here costs more than the board does sometimes. So if you're interested in that, definitely just try it out. There's tons of resources. I figured out how to do it with a new language, a new build environment, a new architecture. There's tons of resources out there. So if you're interested, get involved. If you're interested in what I'm doing, of course, like and subscribe. Thank you very much.